Today we are going to begin a new chapter, that is on the network models. And in this network models, basically we are going to discuss first of all different graph theoretic concepts, and after the graph theoretic concepts are discussed, specifically the what is a graph and the different components of graph, and thereafter the tree and specifically the spanning tree concepts, and finally after all these basic graph theoretic concepts and their uses, we shall specifically take up two kinds of models. One is the flow models and the other one is the shortest path models, right. Now these basic graph theoretic concepts, that is our first thing, the introduction to graph theory, which is basically used in the network models. So basically the first and foremost topic will be, first of all, what is a graph, right. You see, as you can see in this particular diagram, a graph G is a set of vertices and edges, right. So if I look at what is a graph, so if I look at this essential concept of graph theory, then we say that a graph is a set of vertices and edges. So this is a vertex, this is an edge, this is another vertex. So V1, V2, and this is an edge E1. Let us take another vertex V3, then we have another edge E2. So is this a graph? Answer is yes. Maybe let us call this as graph G. Now within this space, let us draw another graph. Suppose I have 1, 2, 3, 4 vertices. I connect these two and I connect these two. So I have V1, V2, V3, V4, E1, E2. Look at the whole thing. Is it a graph? The answer is yes. Yes, this is a graph. So this is a graph, this is also a graph. So some of you might be thinking that a graph has to be what is known as connected all the time. So this is a graph definitely, but not connected, right. So it is a disconnected graph. A disconnected graph has got components, right. So this is a connected graph, and this is a disconnected graph with two components. Each component is a connected graph. So in a sense, look here, this graph has got two subgraphs. Graph G1 has two connected subgraphs called components. Graph G1 has got two connected subgraphs called components. Now within this I will draw one more graph, graph G3. Is it a graph? Just one vertex. Answer is yes, it is a graph, right. It is a graph of a single vertex. It is not necessary that graph must have edges, not required. Now, extreme case, graph G4. I have drawn nothing. Is it a graph? It's very interesting question, that it is also a graph in a sense, and it's a null graph. So, in the slide, that is exactly what I was written. A null graph is a graph with no vertices and edges. That's called a null graph. But what to do with a null graph? Really, we have nothing to do with null graph. So, therefore, it is just a conceptual thing. We will not discuss about it. Now, why graph theory? Why do we study graph theory? Several problems, kind of problems that we can actually study by making use of graph theory. So, let us look at those usage of graph theory. Number 1, say an utilities problem. Utilities problem. See, we have it, first of all, a graph, or sometimes the graph may be called a network if we might think to have a flow between them. Say these vertices are really representing some junction points, and these edges E1, E2, E3, E4 is some edges, in each edge, suppose this may be a drainage line, and in this drainage line, on this several houses, their draining system is connected, right. So, you have to maintain a certain amount of flow which comes here and say goes out from here. Now, as the flow F goes, the flow will be divided into this and it will pass through that. If it passes through this edge E1, suppose it has an utility E1, E2, U2, U3 and U4. So, an utility problem will really ask, how should I assign the flow so as to maximize my utility? As I put that flow should actually increase my or maximize the utility. The second example could be, let us say, an transportation problem. Could be an example of a transportation problem. So, you see there are several source 1, source 3, source 2, and let us say there are also several destinations, source 1 to several destinations. And what we have to do, we have to send materials from source to the destinations, and there are different paths that are available, right. So, I am drawing in different colors so that it does not become too juxtaposed. So, these are S1, S2 and then from S3 as well, right. So, you see that from these 3 sources we have to send materials to these 4 destinations, and each of these path has got a certain amount of cost, and at each of these sources there are some availabilities, and here there are some demands. So, AIs and DJs. So, each source has got certain available material and each destination has a demand. So, which paths are to be used to send this material, and how much material should be flown through that? That is the essential idea of a transportation problem. So, you see, perhaps you have solved those transportation problem through linear programming route, but you can also have a network route to solve this problem. In fact, you can also have a network based linear programming method to solve this problem. Apart from that, there are several other kind of problems like electrical network problem, the seating problem, the flow problem, the allocation problem. A very interesting problem is called the social network problem, right. A particular social network can be actually built with the help of maybe several entities. How are they related to each other? Suppose think of a share market. In this share market there are several companies, and they have based on the share market prices, their values are changing with time. So, if you calculate some kind of correlations between two companies, how their prices are changing, and if you find a certain amount of correlation, then you draw a line. Means the behavior of these two companies are correlated, and then we get a resulting graph. This graph we can call a social network graph. We can really analyze that social network graph and really look how dynamically it changes over time, and we can predict a very interesting phenomena about the share market. So, like this there are several uses of graph theory. As I said, our discussions will be basically based on only on certain aspects, to be more precise, to the network flows and to the shortest path problem. See, I have not touched upon several other problems like bipartition graphs, the coloring of graphs. There are several very good applications that are available on the computer science literature. This particular course, the network treatment that we are going to give, is not meant for those kind of students. It is meant for those kind of students who are interested in network flows and those who are interested in shortest path algorithms, specifically in the linear programming or operations research literature, right. Having said that, let us go into further discussions. Now, once we have said that what is a graph, the next point that comes is what is a simple graph. A simple graph is, see, when we talk about the graph, then the graph is vertices and edges that we have already seen, but there could be additional things like there could be parallel edges and there could be self loops. So, supposing we have this particular connections. So, you see V1, V2, V3, E1, E2, E3, E4, E5. So, look here, here is a graph. This graph is having 5 edges and 3 vertices. Now, can you see that there are some parallel edges the edges are between same two vertices. So, if a particular edge begins and ends, right, begins, these two edges, the begins at the same vertex and also ends at the same vertex. So, they are called parallel edges. This particular edge E5 begins and ends at the same vertex. So, this is called a self loop. It is practically, there are many situations when you can have parallel edges as well as self loops, right. So, there are situations, but there could be other situations where we have a graph that do not have parallel edges or self loops. Those kind of graphs are called simple graphs. So, what is a simple graph? A simple graph is a graph that does not have parallel edges or self loops. So, like this one is a simple graph. Right, it's a simple graph. So, here slide also you can look at that this is a simple graph and this is not a simple graph, because it has parallel edges and self loop. Is it all right? That is a simple graph. Now, this is another example of subgraphs, right. So, if you look at this particular graph G, then you can see that it has got one component here which is G1, maybe this is another component G2, and this is also another subgraph, because this and this. So, they are, all of them are called subgraphs. So, this is about subgraphs, that subgraph is a subset of the graph, that means every vertex and edge of a subgraph has to be also available in the graph itself. If that happens, then it is called a subgraph, right. So, a subgraph is a subset of a graph. Now, comes the next important point about the incidence and adjacency. So, incidence, right. So, what happens? We have a graph E1. So, what happened? This edge E1 is an incident on the vertex V1. Is it all right? And also these E1 and V2 are adjacent. So, V1, E1 and V2. What is their relation? E1 is incident on V1 and V2, right. And otherwise we call that V1 and V2 are adjacent. That is called adjacency, right. So, V1 and V2 are adjacent. Why? There is an edge between them. All right. So, that is the incidence and adjacency. So, E1 is incident on V1 and V2. Then comes a very important concept, that is the degree of a vertex. Degree of a vertex, right. So, you see, suppose we have a graph, let us say this is a graph So, we have a graph of 4 vertices and I have not labeled the edges. Let us label the edges also, the E1, E2, E3, E4 and E5. So, we have a graph of 4 vertices and 5 edges. So, how many edges are incident on a given vertex? That is the measure of the degree of that particular vertex. So, how many edges are incident on V1? Number of edges incident on a vertex. So, what are the degrees? So, what is the degree of V1? What is the degree of V2? What is the degree of V3? Right? And what is the degree of V4? Right? So, supposing we need these degree values to be obtained. How many edges are incident at V1? There are 2 edges. So, this is 2. At V2, 3. At V3, 2. And at V4, 3. So, this is how we compute the degree of a vertex. Right? Now, let us look at very important concept, that is the isolated and pendant vertices. If you look at this particular graph, there are 2 graphs one graph P. In this P has got how many vertices? There are 5 vertices. What are they? U, W, X, Y, Z. Is it all right? Now, U is having no edge connected to that, so it is an isolated vertex. And W and Z, their degree is equal to 1. That means they are extreme edges, right? That means only one edge is connected, so they are called pendant vertices, right? So, this point might be required at some point of time. Now, a very important concept, that of isomorphism. You see, the essential idea of isomorphic graphs, you see, we call 2 graphs as isomorphic if they have 1-to-1 incidence between their vertices and edges. So, this particular example, look at very carefully. W, X, Y, Z, right? They are connected in a certain manner, and here also A, B, C, D. They are connected in the same manner, although they do not look exactly same if you just look at them. In simple words, W and X is connected, A and B are connected. So, W corresponds to A and X corresponds to B. Is it all right? Similarly, X and Y and B and C. X is connected to Y and B is also connected to C. Similarly, Y is connected to Z and C is connected to D. So, these 2 graphs are isomorphous, right? That means, although they look different, but they have the same 1-to-1 relationship between their vertices and edges. So, that means 2 isomorphous graphs, not only they should have the same number of edges and vertices, but the way they are connected will be exactly same, and degree, definitely the degree of the vertices should also be exactly same, corresponding degrees. A particular type of graph is called the so called Petersen's graph. So, you see a very interesting graph is this particular one, the Petersen's graph. What is really happening here in the Petersen's graph, if you really look at that, if you start from any vertex. So, this is called a Petersen's graph. If you start from any vertex, you want to reach any other vertex, it will be the distance or the path will be exactly 2. The path length will be exactly 2. So, supposing you are in this vertex, you want to reach this vertex. Just see, you have simply to go like this. Suppose you have this vertex and this vertex, you have to go like this. You have this vertex and you want to reach this vertex, you have to go like this. So, you can see that each vertex is connected to every other vertex in a two connected manner. So, that is the beauty of a Petersen's graph, and with 10 10 vertices and how many edges, just count the edges, 1 2 3 4 5, then 6 7 8 9 10 11 12 13 14 15. So, with 10 vertices and 15 edges, let us say very interesting arrangement, and if you can connect a graph with 10 vertices and 15 edges in this manner, you can really find that everything is too connected with everyone else. It is at least too connected. Obviously, there are different vertices, they may be just connected, one connected you can say. Is it all right? So, that is the good thing about the Petersen's graph. Petersen's graph also have 3 isomorphic forms, right. You can look at this slide again and again, and you can really try to put those 10 vertices numbers, the similar numbers, like if you call it A, B, C, D, E, then E, F, G, H, I, try to put the same A, B, C, D, E, F, G, H, I, J, A, B, C, D, E, F, G, H, I, J. So, put the same numbers in these graphs also and see that they have the same incidence. In other words, these two are also Petersen's graph, right. They are isomorphic forms. So, these isomorphic forms are sometimes good to really understand and identify, so that it helps us in analyzing systems in a simple manner. Now, edge and vertex disjoint subgraphs. You see, sometimes when we have a particular graph, we may be able to find out edge and vertex disjoint subgraphs to really understand edge and vertex disjoint subgraphs to make better understanding of a problem. All right. So, you see, suppose I have a graph here. All right. So, this is V1, this is V2, this is V3, this is V4, and here is E1, E2, E3, E4, E5 and E6. So, if I draw like this, right. So, look at very carefully, this is graph G. The graph G is partitioned into two subgraphs G1 and G2, and they are edge disjoint. What is the advantage? That if we can really make this kind of subgraphs, we can partition a problem, right? And if this represents the total problem, these two are representing two partitions where there are no common edges. Yes, vertices are common, but you can still make very interesting observations out of such situations, right? Similarly, we can also have vertex disjoint subgraphs. So, maybe we can make say V1, V2, this is one connection, and V3, V4, this is the other. So, you see here we are not able to partition the whole thing, but at least what we have done, we have got two vertex disjoint subgraphs we have obtained out of that graph, right. So, we stop here now, and we shall continue with our discussions in our next class. So, thank you very much.